Hi everyone. Today we'll discuss about specific energy in case of open channel flow. So we know that from the Bernoulli's theorem, the total energy in any flow, that is in a pipe flow, the total energy is nothing but the uh, sum of pressure head and velocity head and the datum. Okay, so the total pressure is nothing but pressure head plus velocity head and the datum head. See, let me take the open channel now. So this I'll take it as the channel bed. And this I'll take the free surface of the water. Here free surface of water in case of open channel is nothing but a hydraulic gradient line. So above the hydraulic gradient line, there is what? Total energy line, that is nothing but the velocity head v square by 2g. I take d as the depth of the channel. This is the bed of the channel. So here what happens in case of the open channel, the pressure at any 2 point is nothing but what? Atmospheric pressure only, because it is open to the atmosphere. Therefore, the pressure is atmospheric pressure. So therefore, in total energy, I'll remove this one, that is the pressure head. The remaining is velocity head and the datum here. So if I consider the channel bed as the datum, if I consider the channel bed as the datum, then the energy corresponding to this, that is by taking the channel bed as the datum, the total energy in case of open channel is nothing but the sum of the depth of flow and this what? Velocity at, that is d plus v square by 2g. This is called as specific energy, that is specific energy E is equal to d plus v square by 2g, because I have taken the datum at the channel bed. So what is the definition of specific energy? It is the total energy per unit weight of the channel. It is a total energy per unit weight, taking the channel bed as the datum. Channel bed or the channel bottom as the datum is known as specific energy. Specific energy is defined as the total energy per unit weight of the fluid, taking channel bed as the datum. So understood? So if I take the datum other than the channel bed anywhere below this, that will taken as total energy. Specific energy is nothing but the total energy per unit weight of the fluid by considering the channel bottom or the channel bed as the datum is known as what? Specific energy. In other words, you can also say that specific energy is sum of depth of the channel and what? The velocity head. Now you understood what is specific energy and what is the difference of the specific energy and what? The total energy of the pipe flow. Okay, understood. Next, we'll discuss about the specific energy curve. It is also a very important topic. We'll discuss specific energy curve. Specific energy curve or the specific energy diagram is nothing but the variation of the specific energy with respect to the depth. So let me consider the specific energy equation. It is E is equal to d plus v square by 2g, where d is what? Depth of flow, which is constant. So here I'll take the specific energy is nothing but this depth. I'll take it as potential energy, okay, which is a stagnant in nature because the depth of flow is constant, plus v square by 2g is what? It is nothing but the kinetic energy. So the specific energy is nothing but the sum of the potential energy and the kinetic energy. So specific energy curve, what I'll do is, it is a variation of the specific energy E with respect to what? The depth of flow D. Okay, so by observing this, it is a potential energy and the kinetic energy. This potential energy, which starts from the origin, which is a linear in nature, having an angle of 45 degree with respect to what? The x-axis or the horizontal. This curve is called as potential energy curve. Okay, so this represents what? EP, potential energy curve. Now, the second curve of the specific energy is what? Kinetic energy curve. The variation of the kinetic energy will be like this. It is parabolic in nature. So this curve represents what? The kinetic energy curve. This curve is. Now, since this specific energy is the combination of what? Potential energy curve and potential energy and the kinetic energy. So specific energy curve is nothing but if you add these two curve, you will get an specific energy curve. Specific energy curve. Let me write the specific energy curve. This is the specific energy curve. Okay. So let me give this as A. This is B. Somewhere this point, I'll take it as what? C. So this A, C, B represents the specific energy curve. This curve is the combination of the kinetic energy curve and the potential energy curve or static energy curve. Therefore, we get this. This ACB is the specific energy curve, which is cubic parabola, which consisting of two limbs, that is, one is limb AC, another one is limb CB. This AC limb, which runs almost parallel to this potential energy curve. The lower limb, that is a CB, which is asymptote to the kinetic energy curve or the x-axis. Okay, it will never meet the x-axis in any finite distance. Therefore, I have used the word asymptote. This CB is asymptote to the x-axis. Okay, now what I'll do is I'll take 2 points, that is in this limb and this limb, where the specific energy is same. You observe this, both this point I have taken where the specific energy is same. The depth corresponding to the lower point, I'll take it as D1. This depth, I'll take it as D1. The corresponding to this point, I'll take it as depth D2. So depth is different, but specific energy is same. So the 2 points on the specific energy curve where the specific energy is same, these two depths are called as alternate depth. So D1 and D2 are called as what? Alternate depth where specific energy is same. Now what I'll do is, if I increase this alternate depth, so let me take these 2 points now. Okay, what happens? This specific energy also increases. Let me decrease this 2 point. It decreases and it merges at point C. Both this depth will merges at point C. This point C, okay, is the point where the specific energy is minimum. Where the specific energy is what? Minimum. The depth corresponding to this minimum specific energy, let me write here, the depth corresponding to this minimum specific energy is known as critical depth, which is denoted by D suffix C. The depth corresponding to this minimum specific energy is known as critical depth. The velocity corresponding to this minimum specific energy is known as critical velocity VC. Critical velocity VC. Okay, which is nothing but critical velocity. So critical velocity and critical depth are the depth and the velocity, which is referring to what? The specific energies minimum. I hope you understood. The point C, you observe this point C, this point is called as critical flow condition. This point is critical flow condition where specific energy is minimum. Specific energy is minimum, depth is critical depth, velocity is what? Critical velocity. Okay, so if this specific energy, if it is greater than minimum specific energy, this greater than this area is subcritical flow. The flow is called as subcritical flow. If the energy, if it is greater than this E minimum, if it is greater than this E minimum, so this below this specific energy is known as supercritical flow. Supercritical flow. So if the flow is above this point C, it is known as subcritical flow. If it is below, it is called as supercritical flow. Subcritical flow means the depth of a flow D is greater than the critical depth DC. You can observe the sketch here. The depth of flow is greater than DC. This is nothing but subcritical flow condition or the subcritical region, we call it as. In the subcritical region, you can observe this velocity is less than critical velocity. Velocity is less than critical velocity. On the other hand, if the depth of flow is less than the critical depth, less than the critical depth means this region is, then the flow is known as supercritical flow. Supercritical flow. In this case, velocity is greater than the critical velocity. Okay, now you understood. Okay, what is the point C? The point C represents the minimum specific energy, where the depth corresponding to this point C is known as critical depth, and the velocity corresponding to that point is known as critical velocity. If the depth is greater than the critical depth, then the flow will be subcritical flow. There the velocity is less than the critical velocity. If the depth is less than the critical depth, then this region is supercritical flow. Then the velocity is greater than the critical velocity. This is the specific energy curve. While writing the specific energy curve, you have to write the curve. Then you have to show the point A, C, B, minimum specific energy, then critical depth, critical velocity, and the two depth. One is about one is greater than the critical depth, another one is less than the critical depth, where the specific energy is same. That two depth is alternate depth. You have to write up to this. Okay, you understood. Next, we'll find out what is the expression for this critical depth DC and what is the expression for critical velocity VC. Okay. We'll see what is the expression for critical depth DC and the critical velocity VC. So we know that specific energy E is equal to D plus V square by 2G. Okay, so let me write E is equal to D plus. See, in case of velocity, what we know the continuity equation, that is V is equal to discharge divided by area. Okay, so you substitute that, it becomes, where V square you substitute as Q by A, it becomes Q square by A square into 2 into G. Okay, so therefore E is equal to D plus here Q square I keep as it is divided by area. Let me take this channel section as a rectangle channel. So what is a rectangle channel area? That is B into D. Since it is A square, it is B square into D square into what? 2G. Okay, so you observe these two. This is a discharge Q. This is the width of the channel. Discharge per width is nothing but small q that we have discussed in the previous videos. Therefore, this E is equal to D plus small q square divided by D square into what? 2G. So, okay, this small q indicates what? Discharge per unit width. Discharge per width, discharge divided by unit width is nothing but small q. So let me write like this. E is equal to D plus q square by 2G. Let me take this D square to the top. It becomes D power minus 2. Okay, so here that when actually the depth becomes critical depth, the depth becomes critical depth when the energy, specific energy, becomes minimum. Okay, so for the minimum specific energy, this depth will becomes the critical depth. Therefore, the condition is differentiation of the specific energy with respect to the depth should be equal to 0. Then the specific energy becomes minimum specific energy. Then the depth becomes critical depth. In this condition, depth becomes what? Critical depth. Let me differentiate this equation with respect to the D and equate it to 0. I'll get what? DC. So what is the differentiation of this with respect to D? That is, differentiation of D is 1. This is D power minus 2 is there. That is minus 2 into q square divided by 2G into D power minus 3 is equal to 0. Here instead of depth, I'll write DC because this condition is applied now, and a specific energy becomes minimum specific energy, depth becomes DC. This 2 and 2 cancel. You simplify. 1 is equal to q square divided by G into DC cube. Therefore, DC cube is equal to q square divided by G further dc is equal to q square divided by g whole to the power of 1 by 3, or you can write it as a cube root also. This is the expression for critical depth dc. So dc is equal to what? Q square by g to the power of 1 by 3 in case of a, we have considered for the rectangular channel section. Therefore, dc is q square by g whole to the power of 1 divided by 3. Okay, so you understood this. This is the expression for dc. For the critical velocity, let me take the critical depth expression. dc is equal to q square by g to the power of 1 by 3. So taking cube on both the side, it becomes dc cube, which is equal to q square by g. Therefore, q square is equal to g into dc cube. Okay, so now in place of q square, I have to write with respect to the critical velocity Vc. So let me write here. We know that discharge q is equal to area into velocity. So discharge q is equal to, if I take rectangle, area is b into d into velocity. The discharge q, I will take the width here, which is equal to what? D into v. What is q by b here? That is discharge by width is nothing but small q, which is equal to d into v. When this depth becomes critical depth, the velocity is also critical velocity. Therefore, where in place of small q, you substitute as dc into vc. Therefore, it becomes dc square into vc square is equal to g into dc cube. If you simplify, you will get vc as root of g into critical depth dc. So this is the expression for critical velocity in case of a rectangle channel, that is vc is equal to square root of g into dc. Okay, you understood. Now, what is the relationship between critical depth and minimum specific energy? So I'll write, we know that specific energy is equal to d plus v square by 2g. Now, the specific energy is minimum, then the depth becomes critical depth, velocity becomes critical velocity. Okay, so further, in this you can write what is the VC here. You can see this expression, that is VC is equal to Q divided by DC here. So therefore, that is E minimum is equal to DC plus, in place of VC, I'll replace as Q square by DC square into what? 2G. DC square into what? 2G. Now, you observe this is in place of Q square, I replace with what? DC and G. You observe this equation. What happens in place of in this expression, if I write DC cube is equal to Q square by G, therefore Q square is equal to DC cube into G. Therefore, E minimum is equal to DC plus in place of this Q square by G is there, no? I'll replace this by what? DC cube divided by DC square into what? 2. The square and cube cancel. DC plus DC by 2, that is 1 plus 1 by 2 is nothing but 3 by 2, that is E minimum is equal to 3 by 2 times DC, or DC is equal to 2/3 of minimum specific energy. So this is the expression for the critical depth in terms of what? Minimum specific energy. So critical depth is equal to 2/3 of minimum specific energy. So this is the relationship between the critical depth and minimum specific energy. Next, we'll see the critical flow condition. So let me take an channel. Okay, so I take an, this is the free surface of the water. So let me take a small, that is area at the free surface. This is the small area I'll consider, at the free surface. The depth of this, I'll take it as d. Then the area of the small area, I'll take it as dA. This is T, I'll take it as the top width of the channel at the free surface. So T is the top width of the channel at the free surface, dA is the small area at the free surface, and dd is the depth of that small strip what we have taken at the free surface of the channel. Okay, so from this I can write this area dA is nothing but this total width into what? Depth, T into dd. Keep this on one side. Now we'll move from the basics, that is E is equal to d plus v square by 2g. So that is E is equal to d plus, in place of v I replace by discharge, that is q square by a square into what? 2g. That is E is equal to d plus q square by 2g into a to the power of minus 2. So for the critical flow, the condition is what? The specific energy becomes minimum specific energy, depth becomes critical depth, velocity becomes critical velocity. Correct. So specific energy is minimum, is the condition is the differentiation of the specific energy with respect to the depth should be equal to what? 0. Okay, now what I'll do is I differentiate this above equation and equate to 0 so that the energy becomes minimum and the critical flow condition is applied. So for this is the condition for the critical flow. Therefore, if I differentiate this with respect to the depth, what happens? This is 1. So here q square by 2g is constant, but a that is area. Area is also dependent on the depth only. Therefore, we have to differentiate this. It becomes minus 2 into a to the power of minus 3 into q square by 2g into dA by dd is equal to 0, because we are differentiating this area. Since area is depending on depth, this is the differentiation of this one. So a to the power of minus, differentiation is minus 2 into a to the power of minus 3 into dA by dd into q square by 2g is constant. Clear? Now, what is dA divided by dd? You can observe here, dA divided by dd is what? T. That I'll apply here. That is 1 minus this 2 and 2 cancels here. Remaining is q square. This dA by dd is nothing but T divided by a cube is equal to what? 0. Further, I'll write here. That is q square T. So sorry, this g is left out here. Q square T divided by g a cube is equal to what? 1. So further I can write q square by g is equal to a cube divided by t. Okay, see, this is the condition. If this condition is satisfied, then the flow is called as critical flow. So let me take this as equation 1. So this is the one of the condition. The flow is critical, that is q square by g is equal to a cube by t. Also, you can observe here q square t divided by g times a to a cube is equal to 1 means the flow should be critical is dependent on only the channel geometry and the discharge. Okay, the slope of the channel or the roughness coefficient does not deal with this critical flow condition. This critical flow is dependent only on the channel geometry and the discharge. This critical flow does not depend on the channel, that is the bed slope of the channel or the roughness of the channel. Okay, so further what I'll write here is further I can write, see, I'll just take this q square, I'll take this a cube to this side and I'll write a square into a, which is equal to g divided by what? T. G divided by what? T. Then further I'll write Q square by A square is equal to A divided by T into what? G. Okay. So what is Q square by A square? By the continuity equation, we know that Q is equal to area into velocity, then Q by area is equal to velocity. Therefore, Q square by A square, I can write it as V square is equal to what is area divided by top width. If you remember, while discussing the channel sections, different geometrical properties, while explaining geometrical properties, I have explained the ratio of area of the channel to the top width of the channel is nothing but hydraulic depth D then into G. This D is hydraulic depth, which is nothing but A divided by T. So further, if I write here, see, you observe here, if I take that is V square divided by G into D is equal to 1. Now, taking the square root on both the sides, we have square root of V square is V divided by square root of G into D is equal to 1. This V divided by root of GD is nothing but Froude's number, which is equal to 1. This is the condition for the critical flow. So for the critical flow condition, Froude's number is unity, and one more condition is Q square divided by G is equal to A cube divided by T. This is the one more condition. So if this equation is satisfied, then the flow is in the critical flow state. And for the critical flow, the Froude's number is equal to 1. So while discussing the specific energy curve, I also told about the subcritical flow and the supercritical flow. You observe here, for the subcritical flow, that is, the depth of flow is greater than the critical depth. Okay, so this is called as what? Subcritical flow. In subcritical flow, the velocity is less than the critical velocity. Since the velocity is less than the critical velocity, the Froude's number for the subcritical is less than 1. Froude's number for this subcritical flow is less than 1. Similarly, if the depth of flow is less than the critical depth, the flow is called as supercritical flow. Flow is supercritical flow. For the supercritical flow, the velocity is greater than the critical velocity Vc. If this velocity is greater than the critical velocity, then Froude's number is greater than 1. So for the subcritical flow condition, Froude's number is less than 1. For supercritical condition, Froude's number is greater than 1. If the Froude's number is equal to 1, then the flow is called as critical flow. This is all about the critical flow. For the critical flow, this equation and this one should satisfy. Then the flow in an open channel is critical flow. Okay, keeping the discharge and all constant. So this two will be satisfied. Then the flow is called as critical flow. And also this critical flow, it does not dependent on the bed slope of the channel. It is dependent only on the discharge and as well as the channel geometrical properties of the channel. Okay, so this is all about the specific energy, and thank you so much.